welcome and welcome to what's now my second annual PiDay Eve celebration. So thanks everyone for being a part of this. As I mentioned, at least in writing, I think to everyone and verbally to anyone who I've talked to, the idea with the timing being the day before PiDay is hopefully a bunch of us can get some new ideas that we'll be eager to try out with our students tomorrow. So that was the idea with jumping the gun with the holiday, doing it a day before. And I know I'm going to be eagerly watching everything everyone shares and trying to recreate all of them if possible with my own students tomorrow. I hope everyone's going to be the same. So with that being said, let's get into the experiments. With the tentative order, Carolyn, I had you up first. Are you okay with going first for this?
Absolutely, really delighted to be there this afternoon. Can you hear me all correctly? All good?
I can hear you loud and clear, yeah.
Perfect, excellent. So, sorry, there we go. Before I go into my presentation, I just want to show you what I've basically cut out of what I would expect to have a piece of wood, but my circular saw wouldn't work. So there we go. So we have a lovely square of a certain thickness and a lovely, circle here cut out of polystyrene, but it would work much better with a nice piece of homogeneous wood, and I've called it weighing pi. So if I now share with you, just in a minute, there we go. So if I share my screen, weighing pi, okay, can you see my screen now?
Yes, coming through clearly, yes.
Perfect. For this experiment, basically you have a square piece of homogeneous material of dimension called 2r. For a square, we'll have the area of the square of 4 times r squared. And we're going to put it on the scale and get the mass out of it. So I'm going to call it ms. Then out of the same material, or even within this square, you can cut out what doesn't look like a circle anymore on my screen. So a circus of radius r. So the area of the circle will be pi r squared. The mass will be called mc. So we put this on the scale with the students. And when we weigh pi, if my order was correct, because it's an homogeneous material, the mass is proportional to the volume and its density for the square and for the circle. So if you do the ratio between the mass of the circle and the mass of the sphere, you will end up with basically the value of pi over 4. So that is a way to basically, inverted comma, weighing pi. So this is my little experiment for pi, which I like to do. So there we are. Thank you for having me.
Beautiful, thank you. Does anyone have anything to ask or any feedback on that one before we move on? And I love it that it's a physical thing where you can get students using equipment in the lab, but still the result is something that you expect, so you can compare how close to what you expect is.
Exactly. So, and then if you actually cut the piece of wood yourself, you also need to add the sawdust that you collect. So there we are.
Oh, I didn't think of the sawdust. Does it ever end up
where that makes your uncertainty basically. So I think that's a good one. It works anyway. It worked in the past.
I like that because I normally think of sawdust as being light enough that you don't really need to think of it, but it's
no, you can get a gram of it at least when you do it with a lovely, nice big piece of wood. 1 or 2 grams of this makes a difference. So that gives you your sort of uncertainty on your measurement.
Just taking a step back on this, because I'm thinking of doing it with cardboard just because I have more scissors than I have saws, and with students, and presumably it'll still work whether it's wood or with its cardboard, right?
Yeah, it then depends on the resolution of your weighing scale, of the balance that you use. So you need to have. It doesn't work I wanted to do it with my lovely little pieces of polystyrene. I don't think it works as well as with wood. In school, it worked much better with the pieces of wood I had than this one. The uncertainty is rather big. This is why I didn't actually show the results, because I was like, So try wood if you can, it's better. If not, try a very thick, heavy cardboard box.
This might seem like a tedious amount of questions, but do you have like a, what's it called? A jigsaw or like proper saws in your school? Because in my school, all we have is like cheap €5 saws, which I got from the hardware store.
If you have a circular saw, horizontal or vertical circular saw for wood, that's what our technician used. So, but yeah, it would work with cardboard box if the resolution of your wing scale. So actually, there's quite a lot behind this in terms of discussion with your students. You could even have, in a dream world, you would have the wood, the cardboard, the polystyrene, and see how the uncertainty changes with what you are measuring.
As always, a lot of things to try out. Does anyone have any questions? I've kind of monopolized the questions there, but does anyone have any questions before we move on to the next experiment? If there was a question that we missed, please let me know and we'll go back to that. If not, then I'll queue up David's video. And David warned me he's traveling, so he might not join live, but he sent a video of an experiment of pi with pies. So I should be able to queue that up. Let me know that the sound should be working. You should be able to see David nice and big with balloons in the background. Let me know if that's not the case.
No, we can see.
Perfect. And can you hear him now?
PiDay.
Yeah, sound.
So
perfect. Okay, so we'll see David's PiDay experiment.
I'd not talk about Pythagoras. I'd talk about pies, and I've got some pies here, some experiments with pies for PiDay. So the first one is this, and it's a question: if I get 2 pies and I watch this dot, if I rotate the second pie around the first one, how many times will this pie rotate while I'm going around the other pie? That's one question with pies. And then here's another question with pies, where I'm going to start this pie at this end. You see that? Start that pie at this end, and I'm going to roll it along the length of 3 pies. So 3 pies down here. Will it get to the end before it's done 1 full revolution? So there we are. We've got some experiments for PiDay about pies.
No, Grandad, you've got the wrong kind of pies.
What do you mean? These are the right kind. What pies are you talking about?
No, it's pi, as in the number.
Oh, right.
Like pi, like 3.14159265358979323383279502884.
How do you know that? I don't know. I know 3.142, but that's about all. But let's just check that you've got it right. So if we hold this up, this is a spinning top, and you can see the number pi on that. And tops are a lot to do with pi as well. So we can spin the top and you can see it there. But let's move to our 2 experiments and just hold this so we can see. When you rotate one of the pies around the other, you can see, watch this dot, it turns once, going around halfway, and twice going the other way. So it goes around twice because the curvature of the first pie is the track, so that's one revolution, and the curvature of this one is the second. And then here this is similar to experiment we did last time. 3 diameters, circumference of a pi is pi times the diameter, so it's 3.142. So if we start with the dot just at the end there, and we rotate it, coming around, the dot doesn't get to the end, it's a little bit beyond, and that little extra distance is the 0.1416, etc., as Andrew told us. So pi is about pies, but it's also about circles, and it's also about spinning tops. And there's a lot of pi in spinning tops, but that's another story.
Beautiful. So that was David's 2 pi experiments, and at least one of them caught me off guard slightly the first time I saw it. I'm not going to lie, this is the 2nd or 3rd, if not the 5th time I've seen this video. And one is even foreshadowing on one that we'll probably see shortly. Does anyone have any thoughts on David's before we move on to, I think Maria from Greece is up next on the schedule. Any thoughts about that before we move on?
I think it's lovely.
Oh, okay. And so Maria, are you ready if we switch to you next?
I think so. Good evening from Greece, from Ioannina.
Well, welcome, and thanks for joining us to share an experiment.
Could I share my slide?
Oh, yes, please do. Yes, of course.
We're moving on in a kindergarten. PiDay approaching the PiDay in kindergarten in Ioannina, Greece, with little creative scientists aged 4 to 6 years old. We exploit the science, technology, robotics, and engineering, and arts, mathematics. And here is Ioannina and Klimatia, Ioannina, and our map, and the interactive map we have already created. And our PiDay, we had invited from a e-twinning platform to participate in a project entitled Happy PiDay, and we have created this painting with our students, and diameter and cycle. We made the pie cake, and have designed the circles. Our first connection with the diameter and perimeter and the mathematics, we use understand all these concepts. So diameter is this one, and the perimeter of our cycle is this one line. So we use the B-boat with.
Oh, and I'm sorry to interrupt. There's just a message from the chat mentioning that it's not clear to see the presentation, and it's true. It's not like in presentation mode, so we're still on the first slide if you're trying to have us see the other parts. So sorry to interrupt to mention that.
I'm sorry. Maybe stop the stop sharing and again and try again another time. Is it clear now?
Yes, yes, and sorry I didn't mention that earlier.
So another very quickly the previous slides. This is and from the kindergarten, our cycles and our pie cake. These activities design the activities with the exploitation of robotics, and they measure a diameter of a circle and the perimeter, and they compare the length. The exploitation of the B-bot, which is it's about 15 centimeters. They measure the perimeter cycle with 6 movements of a B-bot, and the diameter with two movements from a B-bot. And they write all the diameter to perimeter 6 movements for the B-bot. It's innovative approachment of B, of measurement of a cycle, suitable for the and all on the three movements for and 6 movements, 1 movement and 3 for the perimeter. This is a video. Three movements. 1 diameter, 2 and 3, and the length of the perimeter. And they compare all of these and other experiments, and all our activities have uploaded to the platform, compare and interact with other schools from schools, and we have created a word cloud with who have already learned. Thank you for your attention.
That's really beautiful. That's wonderful to see. So many ways that you're making it accessible to such young people as well.
Next maths and cycles. Thank you very much.
And because like often when I'm talking to teachers and like thinking, especially in my own school, I say, well, like what kind of activities do you have planned? And often the teachers of younger grades, they say, oh no, we can't do things with Pi yet. It's too complicated, and it takes a lot of effort to say, well, no, like there are things you can do. So it's really wonderful seeing the wide range of things you can do. You said some of your stuff, your school had shared on word cloud and shared with other students?
Yes, all the new vocabulary we have achieved. We create often a word cloud with the new words of our learning activities. I think that every every section of learn every learning area, it could be taught in or discovered by all ages, even from ages 2, 4 to 6, and I think is the beginning for the learning tip.
Oh, that's really beautiful. Your students are very lucky to have such an enthusiastic teacher making things like that accessible right from quite a young age. It's really great to see. Does anyone have any feedback or questions for Maria?
I think it's nice the way she used the little toy as well for a measurement. The movement of the toy along each path, and was able to count how many times it moved. I thought that was really nice and would encourage students. Yes, thank you.
Thank you.
And so next up, we'll go over to Ireland with you, Paul. And I have your video queued up, but you said you also have something you want to add. Do you want to have the video first or the live part first?
Yeah, yeah. Play that video, even though I hate looking at myself. So,
well, you can turn your screen off, or you can look away for the 4 minutes and 8 seconds that the video lasts, if you want.
I'll manage. Go ahead.
Okay. And like usual, let me know if I haven't queued it up and don't have it playing correct, but there should be Paul that appears, and this sound, I think I checked the box. If you don't hear him within a couple seconds, let me know, and it's that I messed up the setting.
You can do with your students.
Can you guys hear Paul's voice?
I have here a tube.
Yeah, it's good.
With 3 tennis balls. Ask your students, which is the greater distance from the bottom of the tube to the top, or the distance going around the rim? Many students, I think, will suggest that the height of this tube is bigger than the rim. I'm going to take off the label, but we will use it in a little while. And we are going to measure the height of the tube. Okay, it's that distance there. And if I bring it around and compare it with the rim, you can see that the rim is much longer. I can do this also with my hand. I can just about reach the top and the bottom with my hand extended, but if I grasp the rim, then I can't go fully round. And now for a little bit of mathematics. Let's say that each ball has a diameter of d. Let's just call it d. I don't know what it is, but let's say it's d. So that's 1d, 2d, 3d. So the height of the tube is 3 diameters. Now the distance from here across to the other side is also a diameter, but the circumference is 3.14 times the diameter. And so mathematically, the rim length is bigger than the height of the tube. Do you remember the label that I took off? It went around this distance and just about closed. If we are right in our thinking and we line it up, you can see that the label is actually longer than the height of the tube. Now, this phenomenon, an optical illusion, happens with many cylinders. It may be because we're not very good at judging curves. This is another cylinder where you can try out the experiment. You can see that is the height. Okay, but yet there's the width. I hope you have enjoyed this experiment. So that was my experiment. So I don't know if there are questions, Michael, or has everyone fallen asleep?
No, I loved it, and like for me, even though I knew what to expect, the label surprised me at the end. Like I knew what to expect from it, but I just didn't think of it together that way. Yeah, no, it was beautiful.
Okay, if there are no questions, will I show something else?
Yeah, if you're up for it,
Okay,
definitely,
yeah.
yes.
I really liked Caroline's experiment, and it got me thinking. So I don't know, can you see my screen or pin me?
Yes, I'll spotlight you, so it should make you bigger for everyone.
Okay, that's perfect. So this is Play-Doh. Okay, it's modeling clay. Okay, so my question for everybody is, if I was to take some of the Play-Doh and make a sphere from both, what fraction would this one have to be so that the diameter of the big one is twice the small one, the diameter? And just to help people, I've put in some choices into chat, and one of these is the right answer. So the question again, and I hope everybody can understand it, what fraction does this one have to be so that the diameter of the big one is twice the diameter of the small one? If people would like to type their answers back in the chat, it's a bit of fun maybe. One of those answers is the right answer. So I put in 1/3, 1/4, 1/8, 1/2, 1/9. Michael, do you understand the question?
I believe I understand the question, but I actually have a disambiguation like question to ask you. So is it what fraction of the total amount of modeling clay, or
Correct.
what fraction compared to the big one?
No, of the total.
Because I have two different answers amongst your choices depending on what
okay.
the
of the total.
Of the total. Beautiful. Should we get people to press enter on the count of 3 or something like that?
Yeah, you counted. Yeah. On the
count. Okay, so I know I have an answer written. Hopefully everyone else does. We'll count 3, 2, 1, and then everyone who has an answer push enter.
Perfect.
Okay,
Sounds
3,
good.
2, 1, go.
Okay. You went for 1/9. Okay, we've got 1/4, we've got 1/8. Caroline is saying 1/9. Anybody else? Okay, those of you said 1/9, including you, Michael, are correct. Now, I don't know, can you see this? Because in a hurry, I described what was going on. And what I like about pi is it's everywhere. And sometimes we don't have to calculate what the pi is because it's everywhere. So in my solution, I have two spheres and I've looked at the volume of each, and they need to be in the ratio of 1:8. So what I would need to do, this one has to be 1/9 of the whole amount. So if you had 90 grams, you would need 10 grams for the small and 80 grams for the big one. I hope people can follow that because I did it in a big hurry.
It seems very clear to me. Does anyone else have any questions for it?
It's quite surprising that you only need 1/9 of the whole amount.
It does feel counterintuitive. It's just like measuring the length and the diameter. It feels so counterintuitive. So this is why they are beautiful. Thank you.
You're welcome. That's me finished.
Perfect. So moving on, just checking back the order, we should have Merhaba from Turkey, but I haven't seen him join. If you're here but under another name, please let me know. And then after that, I think Astrinos said he had an experiment, but he appears to have walked away from his computer. So if we don't hear from either of them, I'll jump ahead with mine. But if either Merhaba in Turkey or if Astrinos, if you're back around, if not, I'll jump ahead with mine. Oh, and it looks like Astrinos is back. Let me know if you want me to go before you or if you want to go first. And similarly, if I appear to have missed anyone else who thought they signed up, I think I'll be the last one. Or again, if Astrinos, do you want to go before me or after me? And you appear to be muted.
Yes, I guess before you.
Perfect.
I don't know. It's
is now a good time for you? If not, let me know and I'll go first. Either way, it's fine with me.
Okay. I don't know if you can see everything on my camera, but I will try. So. First of all, I have to say that I'm not very fond of pi in terms that when I was taught in mathematics, it was something strange for me because there is always an uncertainty in the measurement of circumference and in diameter. So there is one irrational number getting involved, and I just couldn't. Of course, now I have a better idea how pi appears in unexpected ways. But okay, yeah, it's I have it's not. I'm not going to show an experiment. It's well, somehow an intervention because of two different cases that pi appears out of sudden, and it was really exciting. The first was something called the needle experiment. I hope that, for example, if I have a page which I divide in, let's say that I have needles, some needles that have a length of 1L. and I drop them in a random way. For example, some needles will be like this, and eventually some of them just are on these lines. Remember, this is from this point to this point is 2 times L. L is the length of one needle or one toothpick or one match, anything. And if you calculate, of course, this is not, it's not the scope of this experiment here. If you calculate the probability of one needle or toothpick or anything, just to be on one of these lines, and you count, let's say you drop, for example, 1,000 needles, if eventually you will have about something less than 300 going somewhere, I mean, crossing the lines. So if you divide the total number of the needles by the number of those that cross the lines, you get a number which is approximately 3.1, 3.12, something like this. And the more needles you put in this random way, the better the approximation of pi. And of course, it is mathematically proved that you are what you are doing is finding pi by using the probability of one needle to be crossing these lines. This is number one experiment, but my favorite is what I think it's this. If you have multiple collisions, okay, it's I think they are mirrored, but okay. For example, let's say that this body is still, and you have this moving this way, and we assume that we have the ideal case that friction is 0. So there will be one collision. This body will transfer, if they have the same mass, they are going to have one collision, then this will go and collide with, let's say, this is a body of infinite mass, or a wall. And there will be one collision, 2 collisions, and then 1/3 before the M2 goes to infinity. And if this is when they have equal masses, M1 equals M2. If this was 10 times bigger, for example, if this was 1 kilogram and this was 10 kilograms, you would have 31 collisions. If you divide 31 by 10, you get 3.1. And if you do it in, of course, we cannot actually repeat this experiment. It's only as a simulation. You have to make it in some specialized software. But if you get this 100 kilograms and this one, then you have something like 312 or something collisions. You divide by the mass and you get again a number that is approximating pi. Well, that's all. I don't want to keep you more, but this is what was really exciting for me regarding the pi number. That's all from me, Michael.
That's great. Thank you, Astrinos. I'm sorry, I lost track of the second one, how the number of collisions gets to pi. Do you mind explaining that again?
Yes. Well, when the masses are equal, you have 3 collisions. So, okay.
Well, yeah, because once with the one coming in, going to like M2 to M1, M1 against the wall, then M1 against M2, right?
And third, I mean about this mass. It had 1 collision, 2 collision, second collision on the wall, on an infinite mass object, and then a third collision. Okay.
Yes.
But if this goes 10 times more, you have 31 collisions. Of course,
and if it's 100 times more, you'd have 314 collisions.
Yes, something like this. I'm not sure if it was 314. There is a video, but I didn't want to. These videos on YouTube are very long, and I can give you I can put the links on the chat for anyone. Okay, I will.
Oh, okay. No, now it makes perfect sense. I just hadn't. Okay, yeah. No, for me now it makes sense. But yeah, if you have the links, yeah, I'll definitely check them out afterwards. That helped a lot. So now it's clear to me. Does anyone else have questions about that?
But I think you should simulate it in something like interactive physics or some sort of software, because I'm not sure if you can count 314, or maybe the approximation is something like billions of collisions. So it's
and simulating it with real world things, probably after 10 or so, your damping would be big enough that you wouldn't be able to get significantly more. So you'd need to rely on simulating it, I would think.
Yes, in the real world, my students are fine with 3.14, nothing more. And I was fine for a very long time. And because I am not sure that we can measure circumference and diameter with such an accuracy that it makes sense, for example, in physics. Of course, it makes sense in mathematics, and mathematics give something that is very useful and for us. But it's not something that you can easily explain in the classroom. And probabilities. The needle experiment was amazing because I could do it. I mean, I had about 150 needles and just drop them and count them one by one, and it was 3 point something.
Well, and it's one of my favorite activities to do with students, to calculate pi as well, because they love dropping things. And like if you want to model like Buffon's method, which you showed first, I've just drawn on a piece of paper here, and I have a whole bunch of toothpicks that I can drop. And I mean, that's a much more centralized distribution than you want, but if they're randomly distributed, you could just count them. But in my lab in school, and I just discovered that like by accident, it works out perfectly, but the tile floor of the lab is 30 centimeter tiles. And if you measure most standard pens or most standard markers that kids would have in their pencil case, they come pretty close to 15 centimeters long.
Yeah.
So it works out very well if you just grab any kid's pencil case and pretend that you're mad, or actually get mad if you want, or look for a volunteer, but just take all their pencils, throw them on a tiled floor, and if it's 30-centimeter tiles, then get kids to help you count them before anyone picks anything up, and you'll get a reasonably good approximation of pi. And the kids, at least like a lot of the kids I have, they're younger high school or older middle school, and they love it if you just make a mess on the floor and put a bunch of pens, and then you can make some sense of it. So that's one of my very favorite ways to try and get them measuring pi. So I'm really glad you included that one, Astrinos. Are there any other questions or comments for Astrinos before I move on to my experiment to measure pi? It looks like no, and I've made a mess with a whole bunch of toothpicks all over my desk now. So for mine, I'd mentioned in my email, anyone who could bring a section of string, you can help me get a couple of results for this. So I'm going to take a couple of results, and it'll go faster if there's at least one or two of you who have a piece of string who can help. If not, you'll just watch me take a bunch of results for a pendulum. But what we're going to do here is use a piece of string and any mass. I'm going to use a pen as my mass for a pendulum. You could use a bottle of water, you could use an eraser, a cup, anything you want. And if you don't have a ruler to measure it, because I didn't say bring a ruler, I said just bring a string. Most of you either have a phone or a computer with a screen. Some of you might even have A4 paper. And A4 paper is pretty close to 20 centimeters by 30 centimeters. So anytime you need a multiple of 10, you can just use A4 paper to get it. Like if I wanted a 10-centimeter pendulum, I'd look at 30 minus 20. I've got 10 centimeters there. I'm going to start myself off with a 50-centimeter one. So that's going to be two A4 pieces of paper lined orthogonal to each other. And I'm going to measure to the middle of the pen, which is approximately the center of mass. And I'm going to try and get the period of the pendulum. So again, if anyone else can make a pendulum out of a piece of string, if you have one handy, and any weight, pick any length you want, and measure the period of the pendulum. And so measuring the period of this 50-centimeter pendulum, I'm just going to hold it in my fingers. It's not going to be a particularly accurate result, but it'll give an idea of it. And I'm going to use my phone as a stopwatch. I'm just going to start it swinging and count for 10 swings. So 0, 1, 2, 3, 4, 5. Too damped. Maybe I'll only go for 5 swings. Okay, and 12.9 seconds was my period there. If you've made any results for yours, I'm going to share a Google form for anyone who has results to add. Please type in a couple of results, and I'm going to get at least 2 or 3 results, and we're going to use the period of pendulum of different lengths to figure out pi this way. Does anyone have any questions for the kind of results I'm looking for here? And I see a couple of people swinging things, so that's very encouraging. I'll get at least one set of results that's not my own. And in case anyone wants to see what the form looks like, if you're not entering it in yourself, here's my beautiful form where I have a 50-centimeter pendulum. The period of that one was 12.9 seconds. That was for 10 swings, and luckily I checked on data checking, so the actual period is 1.29 because it was for 10, it was 12.9. My initials there. And let's see if anyone else has submitted results. So far there's just results from me. Let's wait till at least one other person has submitted results now. And we can look at the results for this. And if we make a graph of the results, now those of you, and there's a number of physics teachers who routinely join in, so it probably won't be a surprise that the period of a pendulum is related to the length. Can anyone prove that they're familiar with pendulums and either turn on your microphone or write in the chat how the period of a pendulum relates to its length?
Yes, I can.
Okay, Paul?
Yeah, the periodic time is 2 pi times the square root of L over G, where G is the acceleration due to gravity.
Excellent.
How fast things fall. Yeah.
So we have, and as was written, I maybe should have written that bigger, but period is 2 pi times L over G, or pi times 2 times the square root of L over G. So if we take these results, and I'm encouraged that there's a couple more results come in as I keep talking. So if you're still taking more results, do that. And the more results we have, the better. But I'm just going to go ahead and linearize the results for the length of the pendulum. So I'm just going to take the square root of the length here. And then we should be able to get a graph of length versus period of the pendulum. And from that, the slope should give us 2 times pi over G. And all we need to do is divide by 2 multiplied by the root of G, and we should get pi from a graph of a pendulum. And again, if while I'm making the graph, you're still getting results, please feel free to add your results. And the results look slightly uglier than I was hoping for, but hopefully they're good enough that we'll at least be able to get something out of them. Okay, and the slope is around 5. I was hoping for slope a lot closer to 2. Because if we do the math, it'll work out a little bit better that way. Let's see if Carolyn's results suddenly makes the trend line pop to somewhere a lot prettier. Oh, and some more results going in through the chat. Okay, and it looks like from all the results we have, we're still getting a slope that's slightly less than 5. If we plug that into our formula, so we're going to say that pi will equal to the slope divided by, times 2 divided by root G. Root G works out to pretty close to pi, and it was actually one of the definitions for the meter back in the late 1700s. It was the period of a 1 meter pendulum. So it works out that the square root of G is a very good approximation of pi. Yeah, these results aren't working out at all how I expected. If anyone has insight into where I went horribly wrong with this, please let me know.
Michael, did you measure to the center of your pen?
I did. Maybe I wasn't clear enough for everyone to try and do that. It would seem if that was where things went off, it would just be, that would account for the line not going through the origin, but going higher up, which it does, but it shouldn't affect the slope.
Yeah, would you measure to the bottom of the pen?
Sorry, can you repeat that again, Paul?
Would it work better if you measured to the bottom of the pen? Because that was, even though that's not the center of mass, it's a longer pendulum. I'm just thinking.
I'm not sure. I have things to try after this. So this, I'm going to stop sharing my screen for the moment. So I'm really not sure why this worked out so differently than I was expecting. I'll have a think about it and I'll let everyone know what I come up with tonight. But
hi, future me jumping in here for a sec, if I may. I thought about it just after the experiment Sharon did, and I had the axes swapped around, which was a silly mistake. I'm sorry for the confusion that caused, but I thank everyone for their help trying to improve the experiment. As you'll see, with the axes the right way around, we get a value for pi 2.6, which is still like 20% low, not a great value. And all of the ideas and discussions that people had to improve it would very probably improve it. Like I can think of how they work in the right sense for that. But if you're starting with the axes switched around in the first place, it was just a bad setup. So
to backpedal and go with a much simpler activity you could use to graph and get pi from the slope of a graph. Another activity you could use, and with younger kids that works well, if you have them use a piece of string again, but if they get the circumference of a circle, so like circumference around the outside, and they graph that against the diameter, then you'll end up with a diameter versus circumference graph, d versus circumference, where each piece of string, and you don't even need to use like ruled measurements, you can physically tape pieces of string that are the diameter long and the circumference, and you'll find a graph that'll have a slope that just gives you pi with no extra calculations needed. So that's one that works like even for upper primary school students. Maybe I should have just stuck to that one for the moment. Yeah, does anyone have any thoughts on either of those?
Sorry, hi. The last one you talk about it, I know that my friend, she's the math teacher on my school, Teresa, she's not here today. But I know she do this last one activity, but outside. Kids go outside and they look where they can measure the diameter and the perimeter around. So I know that they do, but outside with regular things that we have around the school.
Well, and then you're not limited to the size of things that are in the classroom. Like you could potentially get very big objects as well.
Yeah, they go to the football place where kids they play football. So they go outside. They do lots of things where they drink the water, everything. So it's they enjoy.
Oh, that sounds beautiful. I should bring kids outside tomorrow too.
Yeah, no, but yeah, she has a piece of paper and they have free for half an hour, 20 minutes, half an hour. They go outside, but they have to bring results.
That's really nice. Thank you for sharing. And Astrinos, you said you have a question?
Yes. Well, regarding the pendulum, when I demonstrate Barton's pendulum for the classroom. And of course, when I want it to be as impressive as possible for my students, but the the arc has to be really small. Otherwise, you have a lot of difference between the first oscillation, if it goes really long, and the last one. I always do something like this and calculate the time. I don't know if it is the solution for your for the slope of, but it's not actually the same. If you make the calculation, it's not the period is not irrelevant of the path this way, because it's not you don't approximate the arc with the chord. So the formula is not actually the same.
I think that's a really good point, and something that I overlooked. That and in fact, where pi comes from, it's from a small angle approximation, and
Yes.
why you can get pi out of it. So that very probably has a bigger effect on the results than I initially thought. That if you have a big swing, then the small angle approximation isn't valid anymore.
It should be, of course, for a mean value, it's okay. We don't really care, but it should be something like between 2 or 3 degrees.
Yeah, well, I mean, a good rule of thumb is less than 5 degrees. I think you still have, like, at least for the small angle approximation, for like when it's applied to other situations, I think it's less than 5 degrees. You're still within 2%.
Let's make it 10 degrees, but yours was at least 45 degrees.
Well, and the other thing was, it's a heavily damped pendulum because the mass of a pen is fairly small. And so that's probably going to affect it as well. Like, that affected me deciding to have a much bigger swing than would have been valid, but it's going to slow down the swing as well.
I think what you have done there is you made a double pendulum, which has a different, a chaotic behavior. So you cannot predict. You had one pendulum and the other totally chaotic. You had 2 pendulums combined. So you cannot say it's not the same formula. I have done it with, for example, I did it once with my set of keys. I don't know if, and I was totally embarrassed in front of my students because everything changed. You see, I had movements like this, and I didn't take the whole length into account. So I had actually a double pendulum, chaotic behavior, and everything was wrong. So I had predicted a period of 1.4 seconds, and each time I had a different result. And I couldn't explain it at the same time. So I think you should do it with a different body.
Yeah, with a hevier mass and with a longer pendulum, so I can have
heavier mass only accounts for tension, for string tension, but you don't as long as your string is no. If you have enough weight, it's okay.
Oh, well, yeah, but the more mass you have, the more energy you have per swing, and so the less the effect of damping will be. Like if you think the extreme examples, like a Foucault pendulum, they usually use a several kilogram mass, because then the amount of energy per swing is very big compared to any damping force, whether it's by air resistance or anything else that comes up.
Okay, you can also use a vacuum. You can approximate it with a point mass, but what's the difference? You cannot do it in the classroom. Just get a small ball, and maybe not from a hardware store. I think it will be enough.
This is an experiment not to find pi that we do here in Ireland, to find G using the pendulum. And we have a spherical brass sphere, which is called a bob, B-O-B. But it's aerodynamic as well, so there's less air resistance. But I think, Michael, even if you had a single key, not astronauts' car keys and memory sticks, but a single key, you would get a good approximation for pi.
Yeah, no, I don't think it should be that hard, but I think in trying to oversimplify the materials required for the setup to be just a string and anything else people would naturally have. I mean, I guess most people would have a key handy. But yeah.
Or even this Play-Doh, make a ball, make a sphere.
But yeah, definitely significant improvements to be made there.
Or blue tack. Blue tack. It's nice though. It's good.
And so with that I think brings us to the end of tonight's experiments. Does anyone have any final thoughts or ideas, especially about how people can implement any of these ideas to celebrate Pi in their own school tomorrow?
Well, can I? Sorry.
Yeah, please do. Yes.
It's just a very, very simple thing. You know, kids sometimes don't, when they see an image of the sun, the earth, and the moon, they don't realize the distance. So it's nice to have, like, imagine two balls, one with 5 centimeters of diameter, it's the moon. The other one, more or less 20. In the shops, they sell and they have the measurements, so it's easier. So one with 5 centimeters, the other one with 20. So we have the earth and we have the moon. And then ask the kids with the string to go around the moon 10 times. And they don't, but before that you can ask, okay, so if this ball is the moon and this one is earth, you can put, where do you think the distance is between them? And so the kids normally put like this, very, very nearby. And so they pick up a string, they go around 10 times of the moon, and then they see exactly on scale the distance. And normally they are like amazed with this experiment, well, with this simple demonstration. Of course, the kids, if they are older, we can give them the right, we can do this upside, or how you say this, upside down. So you give them the measurements of the diameter of the earth and the moon and the distance, and ask them this relationship. I don't know if you understand, sorry.
Yeah. No, that's great. And I often do something similar to that, introducing the earth, moon, and sun to students. And one thing I like to add to that is a check that they can see that it has the same angular size. So if they line themselves up on the earth, and like in that case, if it's a 20 centimeter and a 5 centimeter ball, like line their eye up near the 20 centimeter ball and looking at the one that's the moon, if the distance and the diameter of the moon are done to scale, then it should be the same as looking at the moon in the sky. And when you look at the moon in the sky, if you hold an outstretched arm, the moon should be just about the width of your pinky finger and you can cover it. And the same thing happens if you've done the scale right. So if they have their eyes lined up, and this is amusing to see a class full of kids doing this, But if they all line up their eye on a sphere and they're looking at the moon further down, they should be able to see it'll take up the same angular size. And that's a good like body check to see that the model you've done in the classroom works out to scale. And like, of course, if they also have the sun, which offhand, I can't think of if the moon is 5 centimeters, how big the sun would be, but it, like something about 2 meters, right? But whatever it is to scale, if it's been placed a distance to scale, it should take up the same angular size roughly as the moon or an outstretched pinky finger an arm length away. And so it's a good way to check that like all this scale stuff works out and is coherent with what they could observe in the sky on a day-to-day basis.
Can I just jump in then, Michael, just to advertise something which is going to happen on the 20th of March. So you will use Pi for those measurements, but it's called the Eratosthene measurement experiment, and it's done by something in Greece, and it's fantastic. I've done it a few years ago, and I will do it this year if it's sunny enough to have a shadow on the ground, and you link up with other schools and you measure the shadow at just noon in this country, and then you report those measurements on the website I've put on the chat. And I think it's a fantastic little way to get our students to reproduce this experiment in nowadays technology, where you can get results from other schools. So it's a little bit related to Pi, but it's also related to what Ruth just mentioned. So that links up really nicely. Thank you.
That sounds great. And you said you'd put a link in the chat, so.
It's on the chat, yes.
Oh, yes, yes, perfect. And all.
And it's all for free, and you have all the instructions, you know, that explains not just the how to do your measurement, but also the mathematics and how to link up with other schools. And it's just a lovely little way to calculate the radius of the Earth. And it works really nicely.
That's beautiful. I'll try and remember to also share the link when I share a recording of this session with everyone who signed up, to encourage them to do that as well.
Brilliant, thank you.
And that reminds me, usually at the end of these experiment shares, I encourage anyone who has announcements to make, if they have things like that that they want to announce with or share with everyone else. I think last time I forgot, just because a lot of times people don't have things they want to share. But if anyone has anything you want to share with everyone present, please let me know. And after that, then I'll say goodbye to everyone.
I would just like to say that at least 4 of us on this will meet in person in Prague. Ruth is another Science on Stager, Michael. So
excellent.
Yeah, so we should definitely arrange to meet in Prague and have that beer we talked about earlier. And thanks again to you, Michael, for organizing this. It's been great fun, and yeah, keep on doing it.
Well, and anyone who is at the festival, please come by my stand as well to check me out or check it out. And yeah, show support for Team France. And I'm looking forward to meeting a bunch of you in person then. So with that, thanks everyone for joining. Oh, I was going to mention the next 2 experiment shares. Oh yeah, kind of lost for words. So I'd asked people last month and in the sign up for this one if people are interested in an Earth Day or Earth Day Eve one. And I was surprised a lot of people seem keen on that, although I'm not sure how many people want to actually share things for it, because a lot of the people who regularly present things are more from a physics background. So I guess I'm still not sure on that, because I don't want to prevent people who want to share non-Earth Day based things. So I'm still working on that and up for advice or suggestions. there's definitely enough Earth things. Like I've even been teacher in residence at the Canada Food and Agriculture Museum, and they're doing a lot of Earth Day things. So I might do a separate thing rather than like the monthly experiment share, just to not cut off potential ideas for non-Earth Day things. Feel free to let me know if anyone has any input on that. I'm up for suggestions. And sometime in the future, probably in May, a silent experiment share to try and encourage more people who aren't comfortable in English to share experiments. I think that's all I had to say. Anyone have anything else to say before we all say goodbye? Okay, so in that case, thanks everyone for joining, and thank you especially to everyone who shared experiments. Have fun celebrating PiDay tomorrow. Have a good evening, everyone.
Thanks, Michael.